So we got a great question here, from 2009 for me. This is number 3 about experiment design. And I even threw in an optional part C. Now part C is kind of, that's my own portion that I just threw on there, and it's kind of answered in the setup of the problem, but I thought it'd just be a great place to kind of talk about matched pairs design versus completely randomized design, kind of compare and contrast. So we basically got this 7th grade bio class, and we got 24 kids, and the teacher wants to figure out which instructional program is better, if the kids actually dissect frogs or if they do a computer simulation of dissecting frogs. So we need a little pre-test, post-test action, and we want to randomly assign the 24 kids into 2 groups of 12. So we want, half of them working on the computer software, half of them doing the actual dissection. They're all going to take the pretest, and then after they do their respective lab work, take the post-test. Then we can look at the post-test minus the pretest score, and that's our response variable. So first things first, in part A, they want us to describe a method to assign the 24 students to 2 groups of equal size that allows for a statistically valid comparison. Well, if we were doing completely randomized design, we could just number every kid from 1 to 24, then use our calculator or computer software to randomly pick integers between 1 and 24 until we got 12 distinct integers. Because obviously if student number 7 gets picked for dissection, we can't pick student number 7 again for dissection. So we'd have to pick we'd have to pick 12 unique random integers. And once we get those 12 unique random integers using our calculator, then those students could go and be in the dissection group, and the remaining 12 could go in the computer simulation group. Done deal. And that would satisfy the answer for part A. But I think it would probably be better to do a matched pairs design here, more appropriate, because I feel like there's going to be a variable that could potentially be confounding. And that kind of gets into part B. It says, suppose the teacher decided to allow the students in the class to select which program they wanted to do. We've got to talk about the problems with letting the students self-select. Specifically, it says they want us to provide a specific example. So we need to say why the self-selection is bad, but then we also need to give an example of what could go wrong. And then I threw this part C in here. Let's design a matched pairs experiment. So let's check out the answer. I've already talked about A, but I did this as if I was going to do a matched pairs experiment, not completely randomized design. So I said I think the confounding variable here is that could mess us up is the student's current grade. Because when you're all said and done, a student that's just an amazing scientist, young budding scientist, might have an amazing post-test score. But how much of that post-test score would be attributed to, say, the computer program or the dissection versus just the student's already the ability level where he's at or she's at in science at that moment. They might have some abilities that are allowing them to score amazing on the post-test that has nothing to do with either of these 2 methods. So I feel like the best way to control that is, let's take these 24 students and rank them from 1 to 24. 1 is the highest grade in science. 24 is the worst grade. And then put them in the blocks of 2. So the top 2 science students in terms of grade, they're a block. Now this is matched pairs because I've got a block of 2, and these 2 students are as similar as possible. They're both high achievers in science. They're the best 2 kids in the class, in the block. And then the next block is the kids that rank 3 and 4, and so on and so on. So now we can have all the kids take the pretest here, but then for each block we could use, say, our random number generator on our calculator to randomly choose an integer. And if that integer is even, we'll say that the even student gets to do the dissection, and if it's odd, then the odd student gets the dissection. I'm just kind of talking here. I'm not actually seeing what I wrote. What did I do? Yeah, I said if the integer is even, the even-numbered student uses the computer program, or whatever, and then if odd, vice versa. So that'll create random allocation. We've got 2 groups of 12 students working on the computer software and 12 students doing the actual dissection. But it's a matched pairs and allocation as opposed to just the straight up randomly allocating into 2 groups with no blocking whatsoever, without blocking by their grade. So either would be acceptable for this problem, as it was stated on the AP exam. I just wanted to go through setting this up as a matched pairs experiment, so I wanted to talk about C. So for part B, so obviously allowing students to self-select groups, that removes randomization. I think I wrote this wrong here. By allowing the students to self-select groups, randomization, yep, which is a key principle of experiment design, is no longer present in the design. Again, so one major principle of experiment design is randomization. We're taking that out of the experiment. That's bad. Randomization helps control lurking variables and bias. But now, with that being said, we need to provide a specific example for how this could occur. So I said, okay, consider this possibility. All the best students that are truly interested in science and have the best grades choose to do the dissection. The rest of the class chooses to do the computer simulation. So now let's say we look at the pre-test and post-test scores, and the post-test minus pre-test turned out to be a huge and amazing for the students that did the dissection. But how can we be sure that that achievement is attributable to the dissection and not just attributable to the fact that those were all the kids that really like science, that already have great grades in science, that may have study skills that are kind of helping them beyond what the particular laboratory exercise was doing for them? So we'd get this confounding effect. So that's where I think having my match pairs design, it kind of helps control that confounding. So again, I just finished that up here. So how could we tell if their success is due to the dissection process or their current study skills and work ethic? The student's current prowess in science would be confounded with the effectiveness of dissection as a teaching tool. So I'm specifically giving an example of when you remove randomization, what could go wrong, what sort of confounding effects could be and bias could be introduced into the results. So now part C, I just wanted to throw that in there. So we've already explained how to do the random allocation for matched pairs. So if I'm designing a matched pairs experiment, so okay, I'm going to say start out by following the random allocation that I outlined in part A already. Great, already done with that. Now I'm going to give all the students the pretest, then have each group of 12 students do their respective activity, dissection or computer simulation, followed by the post-test, and I'm going to compare results. I'm going to look at the post-test minus the pretest. So notice the key ideas here is that I'm talking about randomly allocating into treatment groups, and then I'm specifically referencing what I'm measuring in the problem. I'm making sure that I specifically say we're going to give the students the pretest first, then they're going to do their respective activities, and then we've got the post-test, and then when I say compare results, I should actually talk about the response variable here, because the response variable is the post-test score minus the pretest score. That is the response, and that's what I'm going to be analyzing here. So I just thought that was a good place to talk about experiment design, and also to kind of draw that distinction between part A is talking specifically about how you go about randomly allocating into treatment groups versus part C, which I added on, which is explaining the design of the experiment, which they do actually just kind of go through in the question. But I also specifically wanted to talk about how this would be an appropriate place to do a matched pairs experiment versus a completely randomized design.